All right, hey everyone, welcome back. Today we're going to tackle a really classic coding problem, but one with this awesome little twist. It's called combination sum 2, and it's all about finding groups of numbers that add up to a target. Sounds simple, right? Well, the trick is a special rule that really puts our skills to the test, especially when it comes to handling duplicates.
So let's just frame the core challenge right up front. Picture this. You've got a bag of numbers, and some of them are exactly the same. So the big question is, how do you find every single unique group of those numbers that hits a specific target? That's the puzzle we're going to solve together today.
Okay, so first up, let's get into the nitty-gritty of this combination challenge. I want to make sure we're all on the same page with the problem and, the rules of the game. All right, so here's the deal. Officially, you're handed a list of numbers, we'll call them candidates, and a target number. Your mission, should you choose to accept it, is to find all the unique combinations of those numbers that add up perfectly to that target. And I'm going to say that word a lot today, unique. It's literally the most important part of this problem.
And there are two T rules that make this so tricky and fun. Rule number 1, each number from your list, you can only use it once in any single combination. And rule number 2, and this is the big one, folks, your final list of answers can't have any duplicate combinations in it. This means we've got to be super clever when our starting list has identical numbers. Okay, that's enough theory. Let's look at a real example to make this super clear. Imagine our target is 8, and our list of candidates has a bunch of numbers, including 2 ones. The goal is to find all the unique sets that sum up to 8. Now look at the output here. You'll see 1, 1, 6. That's a totally valid answer, right? Because we had 2 ones to play with. But here's the thing. It only shows up once in our final answer list. That's what we're aiming for.
So, the big question is, how on earth do we build something to solve this? Well, the go-to tool for this kind of find all the combinations problem is a really powerful technique called backtracking. The best way to get your head around backtracking is to think of it like you're exploring a maze. But this maze is made of choices. At every junction, you pick a number to add to your little path, and you go deeper. If you find a combination that hits the target, bam, you found an exit. If you go over the target, oops, dead end. So what do? You just backtrack. You take a step back, undo your last choice, and try a different path. It's this super systematic way of checking out every single possibility.
Okay, so backtracking sounds great, right? It's a solid strategy, but it has a huge Achilles heel. It runs into a massive problem when our input list has duplicates. And this, right here, is the real core of the challenge, what I like to call the duplicate dilemma.
Let's check out a new example that's going to shine a spotlight right on this problem. Our candidates are 2, 5, 2, 1, 2, and our target is 5. You see them, right? Those 3 identical 2s just hanging out in there. So what do you think is going to happen when we just unleash a basic, naive backtracking algorithm on this list?
Well, the problem is that a standard backtracking algorithm is kind of dumb. It's very literal. It has no idea that those 3 2s are basically the same thing. So it'll explore a path using the first 2. Then it'll backtrack and explore a whole new path using the second 2, and then the third 2. It treats them all as unique, separate choices, even though they're going to lead us to the exact same answers over and over again.
And yeah, look at the mess this creates. On the left, that's what we get from the naive approach. It spits out the combination 1, 2, 2 3 different times. But what we actually want is the nice, clean, unique list over on the right. So this is it. This is the million-dollar question. How do we make our algorithm smart enough to avoid doing all that extra, pointless work?
Well, the solution is actually super clever, and I think really elegant. It boils down to a simple 2-step process. First, we sort the array, and then we add a really smart little skipping rule.
Okay, so step 1. The very first thing we do, before anything else, is we sort our input list. This sounds super simple, but it's an absolutely critical prep step. Why? Because when we sort it, all the identical numbers get clumped together, side by side. And this little bit of organization is going to set us up perfectly for the next step.
And just look at the difference it makes. On the left, you've got our messy, jumbled array, and on the right, after sorting, it's so nice and clean. Those 3 2s aren't all over the place anymore. They're all grouped up. This new structure, this is what we're going to use to our advantage.
So this brings us to the big idea, the core rule that's going to fix our whole duplicate problem. It's this. At any point in our process, if we decide to skip a number, we have to also skip all of its identical brothers and sisters that come right after it. This is how we make sure we only start a search path with a given number one time.
So how do we actually put this rule into code?
Well, as our algorithm is looping through the sorted numbers, deciding which one to pick next, we just add one little check. We tell it, hey, if the number you're looking at now is the exact same as the one you just looked at a second ago, and you're at the same level of decision-making, just skip it. Move on. It's that one little if statement, that one little check that unlocks the whole thing and stops all that wasted effort.
Okay, we've got the theory, we've got the logic. Now let's see this thing in action. Let's trace our brand new smart algorithm and watch how it cleverly dodges those duplicate answers.
Okay, so we're going to trace a simple example. Our sorted candidates are 1, 1, 2, 5, and the target's 8. So the algorithm kicks off. It grabs the first one. Our current path is now 1, and we still need to find 7. Cool, so it moves on. It picks the second one. Now our path is 1, 1, and we're looking for 6. You see how this works? It just keeps building the path, one number at a time, and it'll backtrack if it ever goes over the target.
And this is where the magic happens. So think about it. The algorithm has already explored every single possible combination that starts with that very first one. It's done. So it backtracks all the way to the beginning, the main loop is about to start over, and it's looking at the second one. But wait, our special rule kicks in. The code says, hold on, I just processed a 1 at this level. This new one is the same, I'm skipping it. Boom. Just like that, we've completely chopped off an entire branch of the search tree that we know would have just given us duplicates. It's so efficient.
So what we just did there, that's not just a one-off trick for this specific problem. It's a really powerful, reusable pattern you can use for a whole bunch of similar problems. So let's wrap it up into a nice little package you can add to your own coding toolkit.
So here it is, the sort and skip pattern, boiled down into 5 simple steps. Step 1, sort your input, always. Step 2, set up your basic recursive helper function. Step 3, inside your loop, you explore your next choice. Step 4, and this is the secret sauce, add that little condition to skip identical siblings. And finally, step 5, remember to backtrack, to undo your choice so you can explore other paths. That's it. That's your template.
And seriously, the best thing about this is how useful it is. The next time you see a problem about combinations or permutations and you spot duplicate numbers in the input, ding, ding, ding. This sort and skip pattern should be the first thing that pops into your head. It's just a fundamental tool for your toolbox.
All right, so we've totally cracked this problem. But before you go, I want to leave you with a little brain teaser. We just solved the version where you can only use each number once. But what if you could reuse each number as many times as you wanted? How would you change this algorithm to handle that? It's a small change in the code, but a big change in the logic. Give it some thought.